So what I did at the end of last class was a question like this. Say I said sine of theta is equal to root 2 over 2. And I'm just going to word it a little bit different than we did last class. Find 10 values for theta. So what I said was, for trig, the values repeat over and over and over again. This time we're given the answer, and we're asked to find what the angle is. Sine of what is equal to root 2 over 2. So there's a couple things to notice here. First is that you notice that that angle, or that value that we're given, is positive. So that tells us about the quadrant it's in. So which two quadrants is sine positive in? The A and the S. So this is what the positive sign here, or the lack of a sign, is telling us that we land here or here. So we're basically ignoring anything that happens down here. Okay? Now that's not just two values, because we can go around and around and around, and we can go around backwards and hit those lines as well. So there's infinitely many angles that will give us this answer, and we're asked to list 10 of them. Okay. So first of all, we need to say, where does sine equal root 2 over 2? So what is that value? On our table that we've memorized, or on the unit circle, is pi over 4. So pi over 4 is one of the 10. Okay, but there's lots more. So you could do this any way you want, but here is pi over 4. So we're cutting a pi into 4 pieces. Here's our pi, 1, 2, 3, 4 pieces, because we're looking at pi over 4. And we only want in these two quadrants. We don't care about down here, so I don't need to draw the second pi, because we're only talking about the top because of the positive. So here's our start. And as we go around, we hit this line. Every time we hit it, we can write a new value down. So this is the value pi over 4. So theta can equal pi over 4, which we knew already. Now, continuing that, what's this line? So 1, 2, 3, 3 pieces out of 4, so 3 pi over 4. And we can continue. So when we go around again, and this is, I said this last class, but we did it sort of at the end. So let's say we're going to continue around that circle and go back to that first line. Now, you don't need to really add on as much as you could say, okay, well, here's the start. We went all the way around, which would be how many pieces? 8, because there's 4 pi on the top and 4 pi, that's 2 whole pies, right? 8 pieces plus 1 more, 9. 9 pi over 4. Then how many more pieces when we're here to get to the next one? How many more pieces from 9? 10, 11, 2? Okay, and we could keep going around. Now that's what we did last class, but I didn't mention that you could actually get values going backwards too. So here's our start, and what would this one be? That is not negative 3 pi over 4. It's not 3 pi over 4 at all. How many pieces do we go through to get up here? So if this is 1, 2, 3, 4, 5. So how could we write that angle? Negative, because we went backwards, 5 pi over 4. 5, and then how many more pieces to get to this line? 6, 7, negative 7 pi over 4. Let's go around again. 8, 9, 10, 11, 12, 13. 14, 15. There's 8. You could go forward or backwards to get the other one, right? Now I've lost my place here, but we could start this. So let's put one more on each. Okay, doesn't really matter. So here we were at 11 pi over 4. So this is 8, 9, 10, 11. Where do I want to get to? Back over to this line. So this is at 11, 12, 13, 14, 15, 16, 17. What about this one? So we're at 15. Let's just repeat this. So going backwards, that was 8, 9, 10, 11, 12, 13, 14, 15. We were here at 15. 16, 17, 18, 19, 20, 21, negative 21. Okay. So, and you could keep going, okay, and you could actually put these into a little formula, but we're not going to worry about that right now. Okay, so let's do one more like that, and then we'll do the trig identities. Okay, so here I said find two positive and two negative angles for which tan theta is equal to negative pi over 3. So the negative sign's important. That tells us which quadrant we're going to look in. And then the 1 over root 3 is going to tell us the angle that we draw each time to go around. So the negative is going to tell us which quadrant. So C-A-S-T. So we want tan to be negative. Which two quadrants are tan negative in? So tan is positive here and here in the A and the T, so it's negative where the S and the C are. Those are the two quadrants where tan is negative. Does that make sense? And now we're going to look up our value. Tan of what is equal to 1 over root 3? Pi over 6. So you would look back at your table. Tan is not even on here, but tan is dividing. So the 2's cancel, so we have 1 over root 3 for the pi over 6. So pi over 6. So tan of pi over 6 is equal to 1 over root 3. That's not the sign, it's just the number itself. That's the original angle. Now that's not one of the answers in this case, because when we draw them, here's our pi cut into 6 pieces. And let's put our second pi, cut that into 6 pieces. Okay, here we go. So I just cut the 2 pi's into 6 pieces. So we've got our 12 pieces all the way around, right? Which two quadrants do we want? S and the C. Your reference angle, or your reference angle is found between the x-axis and your terminal arm. So it's like that first piece, the lowest piece. So if we're talking in this quadrant, then here is our first one. And if we want down here, where do I draw the line? On here, 1 or 2? 1 or 2? 1. It's always the closest one to the x-axis. So this size is pi over 2, or pi over 6. It's the closest one to the x-axis. So here's our second. These are our 2 terminal arms we're looking at. Okay, so those angles. Now, we go around. So here's our start. If we want 2 positive values, what's the first one? How many pieces is that? 5 pi over 6. So theta equals 5 pi over 6. And then what would the next one be? How many pieces is this? It's 1 less than 12. 12's all the way around. It's 1 less than 12, so 11 pi over 6. And we could keep going around, keep adding however many pieces it is. But we wanted 2 positive and 2 negative. So what about our negative values? So we're going to go backwards. So still at the start, right here. That's where we hit the first one. What would that be? Negative pi over 6, just one piece. And then from the start all the way around to this line. So 6 pieces as to here, that's a whole pi, 7, negative 7 pi over 6. So there's 2 positive values and 2 negative values. Okay? So what you do, you get your sign, you figure out what quadrant it's in, and then you draw that reference angle, and then you just start at the beginning and go around to whatever the question's asking, however many times. Okay, so the next, what you need to memorize for this particular course is not all of those trig identities. Hopefully you did memorize them all, because that will help you later on. But for this course, what we want to memorize are these trig identities. These are the ones you need on the final, in other words. So these three, we could need them in the identity section, but we definitely need them for the trig values. If you want to find secant, you need to know to flip over cos. Right, do the reciprocal. Tan is equal to sine over cos. And then the other two that we're going to have on the final are sine squared equals cos squared plus sine squared plus cos squared equals 1, and sine 2 theta is equal to 2 sine theta cos theta, and the last one I should have written it above, 1 plus tan squared equals secant squared. These two are related. They're the Pythagorean identities. They're like if you draw a triangle, this is the sum of the squares of the two sides, and 1 squared. Same thing here. I remember this with the secant and tan. I always remember the plus sign looks like a T, so it goes plus and then tan squared. If you're trying to remember which is on which side, I always say it's 1 plus. And then if you're trying to remember whether it's a secant or tan, this little plus looks like a T, so they go together. So these are both on one side, cos squared plus sine squared equals 1. This one, people get very wrong. We're not taking that 2 out. 2 is just a different angle. Like if you have an angle of pi over 6, angle of 2 pi over 6 is just a bigger angle. You can't, it's not 2 times sine. It's actually the same answer. It's just in a different spot. So you're not factoring out the 2. You're not moving the 2 out to the front. It's that this value, if you were to evaluate something by putting a theta in here, will actually be equal to this sine times cos multiplied by 2. Okay? So you want to memorize those. And then what are we doing with them? We're simplifying expressions. Okay, so the instruction will say, for example, show that 1 over cosecant squared x plus 1 over secant squared x is equal to 1. So that might be a possible type of question. So what you do is you go to the identities you know and you use them so that you can get it equal to 1. So one technique that works most of the time is just converting everything to sine and cos, because in our trig identities, every single identity, cosecant is 1 over sine. These can be interchangeable because they're the reciprocal of each other. So cosecant is 1 over sine, secant is 1 over cos, cotan is 1 over tan. Right. Yeah, so I'll address that question in 1 second. So, yeah, this, remember, if we have A over B squared, that's the same as A squared over B squared, right? If we have 1 over cosecant squared, that's 1 over cosecant all squared. How come? What's 1 squared? 1. Right? This is 1 squared over cosecant squared. When we square a trig function, we put the square between, like on the trig itself, not on the argument. Okay, so that's why you see it in between on all of these. That's saying the whole thing is squared, not just the theta or the x. Okay. So, in other words, if you see sine squared, that's sine all squared. That's what that means. Where sine theta squared is the same as sine of theta squared. So just the theta is squared rather than the whole thing. Okay, so when you want the trig to be squared, the exponent goes in between, that means the whole thing is squared. Whereas if you see it just on the end, that's just the argument that's squared. Okay. All right, so back to our question. If we have 1 over cosecant squared, well, the identity is 1 over cosecant is equal to sine. And the other identity, 1 over secant, is equal to what? Cos. So if we square those, we have 1 over cosecant squared is equal to sine squared. And 1 over secant squared is equal to cos squared. So you can just square them. So we've got here 1 over cosecant squared plus 1 over secant squared. Don't write the 1. You're trying to end up at a 1. So we say, okay, here's the start. This is the side we're changing. And that's equal to sine squared plus cos squared, which is equal to 1 from the identity. Sine squared plus cos squared equals 1 is one of the identities. And that would be it. Okay, so let's get harder. So we're not taking this all as one big equation. We're taking the side that needs to be simplified and then using identities in a row until we end up with 2 secant at the end. Okay? So that's the process. We're going to take the 4 sine x over sine 2x and change it until we end up with this at the end. Okay, so first of all, since you know your identities, you know that sine 2x is an identity. So as soon as you see sine of 2x or 2 theta, you should automatically be thinking this. It's used more than any other identity, really. A lot. So as soon as you see that, we change it. What we're not doing is taking the 2 out to the front or something like that. That doesn't, you can't do that. So here's the identity. We're going to put it in here. So we're going to rewrite the top. And on bottom we would have 2 sine x cos x. So what happens now? Right, the signs cancel. And what about the 4 and the 2? So we can reduce it or simplify. 4 over 2 is just 2. right? A 2 cancels, and sign over sign is going to cancel.
Is the X in the bracket?
It doesn't matter if it's in a bracket or not. We could do that. There. Okay, so one of the signs cancels, and 2 goes into 4 twice. So on top we have 2, and on the bottom we have cos. One more step. So what did we want it to equal? Secant. 2 times secant. Well, there's the 2. That's good. And what's 1 over cos? 1 over cos is secant. That's an identity. So here's 2 times 1 over cos, which is 2 secant. Sine cubed plus sine times cos squared all over cos can be reduced to a single trig function. I'm not telling you the goal. So now it's more like a calculus question where we're just simplifying these things. We don't really know where we should stop, but we need to stop somewhere that's going to work for us. So here the hint is that it's going to be a single trig function. All right. This one's a bit different than the other ones. Does anyone have any idea? Ignore the bottom. That cos does not cancel. How come it doesn't cancel with the stuff on top? Both terms would have to have a cos in it for it to cancel, right? Regular fraction rules apply. So we can't cancel that. Look at the top has 2 terms. When we've got 2 terms and we're trying to simplify in any area of math, we try to factor. Can we factor anything out of the top? Yes. What do they have in common? They both have a sign. So we're going to say, okay, if we pull out a sign, how many do we have left? Squared, 2. And we pull out a sign here, we'd be left with just cos squared. And that's all over cos. All right, now what? So here we factored, just a common factor. Look at what's in this bracket. It's an identity. What's it equal to? 1. So this is just sine theta times 1 over cos theta. You don't need to write your explanations off to the side. I'm just doing that so you can see where I got that. That was an identity. Sine over cos is another identity. Tan. And that's a single trig function. So going back to our first test, we had a similar question as this on our first test. Now we're just adding some trig into it. And I didn't say anything about the answer, so we're just going to simplify. So, ideas. So on our first test, I'm saying, and you may not have applied this to it, but we had something like this. We did this in class. I'm not sure if it was on the test or not. But you can't take the square root of each piece individually. It has to be multiplied to take the square root of each thing. So we can factor out a 25. You'd have 1 minus x. And now you can do square root of 25 and square root of 1 minus x. This doesn't simplify, but this 25 does. So that would be your answer. And we did have another question that was something like this. 25 minus, say, 16. You don't do square root of 25 and square root of 16 separate. You have to put it together first. And then the answer would be 3. Right? So those are a couple things that are similar here. The first one is closer. So what could we factor out? A 9. Leave the big square root. So we've got a big square root. We're going to factor out a 9. We'd have 1 minus sine squared. Well, this is square root of 9 times the square root of 1 minus sine squared. Square root of 9? 3. Now what about this? Here I left it. But I'm telling you that an identity will help us to simplify this. Which identity has a 1 and a sine squared in it? Sine squared plus cos squared equals 1. That's an identity with 2 of the parts in it. So we could maybe rearrange this so that it had 1 minus sine squared on one side. What could we do? If we move the sine over with the 1, we would have cos squared equals 1 minus sine squared. So 1 minus sine squared is equal to cos squared. And we can take the square root of something squared as just cos. So the answer is 3 cos squared, or cos, 3 cos x. These look pretty easy when I do them, maybe. You really need to try them. And that's why I added that homework, because you'll want to try to do them. Last one. Thoughts? And there's not always one right way to do it either, but there is one thing that you should always notice when you see it in any trig type question, and that's that sine 2 theta. Okay, that's an identity, like I said, it's used most often. What's it equal to? Sine 2 theta is 2 sine theta cos theta. Okay, so that's an identity. Anytime you see that, put that in right away. So if we rewrite this, even if we don't change anything else, this at least will get all our trig functions to have the same angle. They all now have a theta instead of one having something different. Any ideas? What could we do next? What's that? Yeah, so secant squared, there is one with tan in it for secant squared. It's 1 plus tan squared. Not going to help us. Why not? If you replace this with 1 plus tan squared, you've now got 2 factors on the bottom you're actually making it bigger rather than smaller. You're replacing something with only one term with something with two terms, 1 plus tan squared. So we don't want to do that. What you should notice here is that there's tan, secant, sine, and cos, a whole bunch of trig functions in the same question. Can we make that smaller? The first thing I said was convert everything to sine and cos usually helps, and everything can be written in terms of sine and cos. What's tan in terms of sine and cos? Sine over cos. So we're going to replace that one. And what's secant? 1 over cos. So what's secant squared? 1 over cos squared. So we'll put these two in, and then fix it up, and things should cancel. All right, so let's do that. So on top is going to be sine over cos. 2 sine theta cos theta 1 over cos squared. Good practice with fractions. So when we have something like this, whether it has trig in it or not, you want, when you have a fraction over a fraction, you need two single fractions so you can flip the bottom one over and multiply. So how can we make this bottom into one fraction so it doesn't look, the top's good already. Sine over cos is one single fraction. Here, what would we have? This is like over 1, and when you multiply fractions, you just multiply across. There. When you multiply anything by fraction, it's like over 1. You just put it all together as 1. There's no plus signs or anything. It's just multiply top, multiply the bottom. So now we've got two fractions. Can either of them be simplified? Like, look at the bottom one. Can't a cos be canceled out? One of the coses can cancel. So we would end up with sine over cos. And on the bottom, 2 sine over cos. Oh my. So you could notice one of two things here. We can flip over and multiply, because I think that's what most of you would do. But if you do notice sine over cos and a sine over cos, what do I say when something's the same on top and bottom of a fraction? They just cancel, so all we'd be left with is a 2. But let's do this. So when you divide fractions, you take the top one as it is, and you multiply by the reciprocal of the one that we're dividing. So now these are two fractions multiplied, so you can write it as one big fraction. I'm just moving the 2 in front. Remember, this is cos times 2 times sine. That 2 is not attached to the sine, just like it wouldn't be attached to an x. It's multiplied by. So the cos cancel and the sines cancel, and what do we have left? 1 over 2. Be careful you don't say just 2. The 2 is on the bottom, so it would be 1 over 2. Sine cancels, cos cancels, and we're left at the 2, so 1 over 2. So that's it for the